Alright, welcome back. We're going to do another trig example, nice fun trig example, get us thinking a little bit. Okay, here's what we have here, okay? It says the angle is in quadrant 2, so I mean, they're going to get us to think here, and has a tan value of this. Determine the possible coordinates of P, okay? First of all, try and draw this circle operation. Okay, it says we've got an angle in quadrant 2, so I'm just going to shoot one out there. So that's good. A tan value of -4/7. Okay, well, if we drop that down and make our reference angle theta here, what this is telling us, okay, well, if tan equals opposite over adjacent, that means we have -4/7, so -4 and +7. Does this make sense that we can go left and call it +7 and we can go up going -4? Not really. So we have to think about this and realize that this is the same as saying +4 over -7. It's the same ratio. So I'm going to use that instead because that matches the picture. Meaning that this would be the correct way to write it, although the value of the ratio would be the same. We're going 7 units this way and 4 units up. First of all, this is our x value and this is our y value. So for point P, which is on this dot here, where it crosses the circle, we would have a value of -7, 4. That's our x value, or that's our coordinate. Now, here's the issue. That's one coordinate of P. What about another coordinate of P? Are we talking about the unit circle even? We're not, because it doesn't say we're talking about the unit circle. So, I mean, clearly we couldn't be, because first of all, this is 7 units back. The unit circle is only 1 unit back. So, like, I mean, the unit circle is probably way down here, right? We're at -1 + 1. So we're talking about a big circle here. So what are other possible coordinates of P? Well, this is the ratio. We need to keep this ratio standard. So what's another way of writing this ratio? Well, that's the same as 8 over -14. So as long as this ratio is true, then we can find another coordinate of P. So let's estimate here. There's one there. What if so -7 is right here. There's -7. I'll write it underneath the 9 there. -14 would be about here. And +8 would be about here. Okay? So we kept drawing this triangle, and we would have a unit circle that is way out here. Okay? You see, all it is a bigger version of a triangle with the same ratio. You have a 90 and a theta, and then, a 90 and a theta, and then the remaining angle. It would be identically the same this way, the 90, a theta, and then the remaining angle. So we know these triangles are similar triangles, and that means the ratios will be the same, but one's an expanded version of the other. So what that tells us, because the ratios are the same, this also is true, and all it's asking is what's another value of P? Well, this is going to be a value of P on some brand new giant unit circle. And this is 14 units back, so there's our x value. And it's not just 4, but it's 8 units high. We doubled it. We doubled the size of the triangle. So there's a value of P. Okay? We have P1 here, which is -7 and 4. Then we have P2, which is -14 and 8. And without drawing it, it shouldn't surprise you that we could go on to P3, which would be -21 and 12. P4, this is just me expanding the triangle, -28 and 16, right? So all I did is I tripled the size of the original triangle, I quadrupled the size of the original triangle. Anytime you expand this triangle in this fashion, keeping the angles the same, you will always have a similar ratio here. For example, that's that. This one would be +12 over -21. Same ratio, just different way of writing it. And that would be there. And this would be 16 over -28. Same value to the ratio, just a different way of writing it. An expanded triangle brings you to a point way farther out there, as you can see by the coordinate points of P. And I only drew P1 and P2, right? Because I don't have a giant blackboard here, I guess. Anyway, so that really answers our question. How many more can we have? Well, I mean, you could go right up to p infinity. So really, there's infinite p that you could have because you can keep expanding this, expanding the written form of that fraction while keeping the same value. Okay, part 2 of the video, we're going to look at what are the actual sine, cos, and tan ratios of this particular, this triangle set here. All right, part 2 coming up.